Hello again, and welcome to part 2 where we're looking at the production 121GW. Again, this product was produced by UEI and it's sold under the EEV brand. So after reviewing that very first video with my wife, she made a recommendation that we go ahead and mark the meters so you could easily tell which ones were which. So my plan is to go ahead and do that. For this video here, I'm not too concerned. The one on the left here you can see is the prototype, and that's easily distinguished by this piece of paper under the fuse. Again, you don't see that with the production meter. So for this video, what I'd like to do is compare some of the hardware differences between these two meters. Of course, we've already talked about the switch contacts, and again, this prototype meter has been modified. You can see there's a little bit of glue located along this resistor pack, and the original meter does not have that. That's something that I've added. You can also see that I've added this large TVS, and of course that was not included with the original prototype. And of course another change that we had noticed was the addition of a shield. So let's have a look at some of the other differences. Again, the meter on the right being the production meter. You can see the spring. This is again for the shield. You can see how the production meter has a finer pitch than the prototype. Not that that's going to make any difference. So here I have the two schematics again. This is for the prototype. It's dated 5/24 of 2017. And this is the most recent schematic I could find. This is dated 1/15 of 2018. Unfortunately, they've made additional changes to the production meter, and the schematic does not appear to reflect those. So one of the very first changes that I was made aware of was the reference. So we can see on the prototype meter, you can see ZD1 is an LM385BXM-1.2. If we look at the production meter, we can see this is now an ADR 3412. At the time I was running the prototype over temperature, and I had noticed how much that 121GW had drifted. Of course, a lot of people were complaining about the way I was conducting that test, but I had conducted the same test on several other meters. It just so happened that the 121 had a higher drift to it than the majority of the meters that I looked at. So you can see that I've never changed the prototype meter. Just above my thumb, this is the reference. And we can see with the production meter, this is the new reference. So I really have no idea how the production meter is going to behave over temperature. Again, we'll be running that test in a future video. So again, this is the current schematic. And notice to the right of R30, we now have the addition of C58. Looking again at the prototype, again, here's R30, and you'll notice that C58 is not there. It appears that it's a no pop. Another difference, looking at the production meter, you'll notice that C30 is now populated with a 27 nanofarad capacitor. And again, if we look at the prototype, you can see C30 is a no pop. So looking at the prototype, you can see just above my finger, that is C30. So when I was playing around with the various versions of firmware, I was trying to get this meter as close as possible to what the production meter was. So I went ahead and added that capacitor. The prototype didn't include it. If we look at the production meter, again, it's just above my finger. You can see C30 right there. Tell you, one of the interesting things is you'll notice that the silk screen on the prototype is actually a lot clearer than what it is on the production meter. I don't know if they changed circuit board providers or maybe they just have a tolerance on that silk screen, but it's definitely harder to read on the production meter than it is on the prototype. So again, looking at the prototype, you can see there's this D14 and D13, and these were originally a 4007 diode, and these have been changed according to this schematic to D13, which was a SM6T22CA. So here we can see on the prototype meter, just above my finger, again, this is D14 and D13. And if we look at the production meter, again, just above my finger, this is the TVS D13. But you'll notice too that they had placeholders in here for Q1 and Q2. These were always a no pop. So it looks like they've changed the way that they're clamping this section of circuitry. So while I have the meter out, again, maybe this will show up with the camera, but you can see where I've cracked that card carrier. Again, this card holder is not supported. You can see there's no glue. It's just soldered to the circuit board. I'd mentioned how difficult it is for me to get my fingers in here, but I had made a video where I was actually using a pair of needle nose to get this card in and out. To me, that's not an acceptable way to access this card. Again, I'm surprised with the production meter that they didn't at least support this with a glue blob. Of course, they've done that with our crystal. You can see right here where it's blobbed between the beeper. It wouldn't have taken much to just put a blob on this thing to try to help support it. You can see just how flimsy that card reader is. It's not like I'm applying a whole lot of force to this. You can imagine, again, with me taking this in and out with the needle nose pliers like I showed, all it would take would be one slip, and I'd snap that connector right off of the circuit board, possibly tearing traces, and then I've got a bunch of rework ahead of me. You know, and I've chosen not to put a blob on the prototype board, mainly because I don't use the card reader anymore. So the change of the reference and these other few changes here don't really concern me. The biggest change that I see is in this area right here. Again, this is for the 15-volt diode test. Down here we have the power supply, and then we have these couple of multiplexers. And the first thing we'll notice is U14, which originally was on the prototype. That's the one just above my finger. If we look at the production meter, you see that chip has now been removed. But the bigger change is right here. This is D7 and D8. These are these two diodes, which you can see are right across this multiplexer U9. The purpose of these are to clamp this line between the two rails of the multiplexer. And again, if we look at the production schematic, you can see these same two diodes. But when we look at the actual circuit board, notice those two diodes now have been replaced with this clamp. So what they have now is a clamp similar to what you see here with the two back-to-back transistors. Those are referenced to VSS of the multiplexer. Looking at the meter itself, notice the rework. See that big glob right there just above my finger? Right there. See, they have actually glued something down in this place and then they pulled it. It almost looks like they've gone through a couple iterations. Again, they started out with the two 4007 diodes. It looks like they tried to maybe make a different fix, and then they went ahead and added this mezzanine board with the two transistors on it. This is a post dated back on December the 3rd of 2018. This is from Dave at EEVBLOG. The latest meters shipped have hardware changes, a copper shield, which we've seen, and a two transistor daughter board to replace the TVS. That daughter board that he's talking about is the one that's replacing these two diodes. So not a TVS, but the 4007s. But what's interesting, again, looking at that production board and seeing this glue or whatever this is that's on this, I'm not so sure that, along with his email, isn't telling me that they had actually put a TVS in here. And again, that's actually what I had done on the prototype meter. So I think that they probably did try to put a TVS in there at one point, and it didn't work out for whatever reason. They removed it, and they went to this clamp. Again, it's kind of hard to say without seeing all the different iterations of the meter. I'm just going by what he's written in this email. They still use the spacer shims until the existing blank PCB stock is used up. The firmware in its current release is 1.57. The specs have not changed. And again, it looks like the thickness of the two circuit boards, which is the claim, again, that they're going with a thicker circuit board to remove the shim, but these two circuit boards appear to have the same thickness. Again, if there's any question about that, just watch the first video. So there's another thing that's changed between these two meters in that circuitry, and it's not going to be easy to tell just looking at the board, and it's not marked on the new schematics, but they've actually changed the IC in the production meter. So I think he had posted some pictures of the new meter. So I responded to Dave. I said, sure, there's some new shield and clamping, but what's this I see? Is that a TI CD4053B with an absolute V supply of 20 volts? The same part that I've said several times that I went to in an attempt to get the meter to survive some basic transients. It looks like somebody is trying to spoil my fun. If they get the clamping right, this meter should do just fine. So Dave responds, yes, sorry, forgot about that change. So one of the questions that came about was, does that affect the calibration? Dave responds, no, it doesn't. It's a DIY mod if you really want that. I personally wouldn't bother. So the person asked, what basic transients or what voltage levels did you supply during your testing? And so Dave responds, I can't speak for Joe's tests, but FYI, the previous chip passed all the UL Cat 3 standard tests just fine. So let's have a look at the data sheets for the two parts. So this is the data sheet for the original part. This is an HEF 4053B. And let's have a look right here, VDD supply. And you can see it's 18 volts. This is the absolute maximum that this IC should ever see. If you exceed this, basically you can damage the device. So what I had done is I had replaced that part with this one from TI. And this is a CD4053B. So we can see again right here, specifications, absolute maximum rating, supply voltage, 20 volts max. So we've gained 2 volts of additional margin. Now you may say, well, geez, 2 volts, that's not a whole lot, especially when people like me are exposing these meters to several kV, kilovolts, not volts. Well, the whole reason that I changed that was to try to find a way to clamp the meter. Again, this meter has a 15 volt diode test, and the meter doesn't actually put out 15 volts. It's something a little higher than that. I think this meter was actually putting out in excess of 16 volts. So when I was supplying a high voltage transient to the front end of the meter, it's carrying through this resistor here, and essentially it passes through D7 for positive transient. And you can see basically how I end up blowing that multiplexer out. So basically what I want to do is clamp this input so it can't force this voltage to exceed that 18 volts. Well, because we already have 16 volts coming out of this power supply, so a lot of the TVSs that I was looking at, they would start to turn on below the voltage that the supply is putting out for the diode check. So what I was looking for is a higher voltage part that would allow me to clamp this thing just above the 16 volts and still have enough margin where I could save the multiplexer. So if you look at what I had posted, I said changing the CD4053 in and of itself would do nothing to improve the meter's robustness. We were talking about a couple of volts versus thousands of volts we were applying. The problem is coming up with a clamp that is not so low that it interferes with the high voltage supply used in the diode check, yet it can't be so high that it allows us to exceed the absolute rating of the mux. You have 15 to 16 volt supply with an IC rated for 18 volts, absolute max. Increasing this margin a couple of volts eased the effects of sorting out the clamp. I'm hoping that what led them to use the TI part was to try to improve the meter's robustness. I won't know how it behaves until I run one, which is the whole point of this video series, right? I'm basically wanting to know, after 2 years and having spoon-fed them essentially, this is how to solve some of these problems and what the weaknesses are of the meter. What did they do with that information? Did they improve the meter or not? So that's what we're here to answer. The video for the prototype is still online. It was first damaged with a 2 kV peak, 100 microsecond full width half height with a 2 ohm source. There were a lot of low-cost meters that were damaged at these low levels. For those wanting to point out the 87V as being the gold standard, make sure you check all the facts first. Again, the data is here. Again, I give a link to where I'm storing that data. So of course this prompted me to buy a brand new 87V. I ran that through all the same transients as I did with the original 87V, and the meter performed quite well. All the Fluke products that I've looked at, except for that one 87V, performed very well. So what I ended up doing was a complete analysis of that original 87V to try to figure out why it failed at such a low voltage. If you watch those videos, you saw where I basically went through every little piece of that circuitry, and in the end, we ended up retransient testing it, and the meter performed quite well again. So to this day, I still can't tell you why that meter performs so poorly, compared to the new one or every other Fluke that I've looked at. I don't have an answer for it. Maybe it was some debris on the circuit board that caused it to break down. I really don't know. It was an old serial number, but I've tested other old Flukes before and have not had a problem. Of course, one of the most recent ones being that black 189 that I ran through the ringer, and even that meter performed quite well, and you could see how badly that thing had been abused. If you're going to make the claim that your production meter is as good as what that 187V was, that obviously had a problem, and that's your benchmark for saying that this is a good product, for those of you who have been following this series, you may remember that I set that brand new transient generator up for about 6 kV, and the whole reason that I chose 6 kV versus something higher, because that was where that 1 amp probe meter was damaged at. Again, that was my runner-up meter in my $50 meter shootout. And again, I thought if your meter can't survive to the level of that cheap amp probe meter, it's not a very robust meter. So that's the criteria I've been going off of. So again, the 121 didn't survive anywhere near that. A lot of cheap meters don't. Hopefully they've taken that to heart. It looks like obviously they've made some changes in that front end. Again, we'll repeat all those same tests and we'll see how this thing performs. Here you can see I've marked all 3 meters. The one on the right is the prototype, which has the pink label. We have the production 1 and production 2 with the green and yellow labels. Again, I've added these to help you keep track when I'm running these tests, which meter is which. So with the 3 meters back together, there's a couple of things I want to show you. One of them is you can see that the housing for this banana connector is split. Again, obviously I use a lot of unshrouded leads when I'm testing these meters, so it is possible that I put some strain on this that cracked it. It's kind of surprising because, you know, I've tested a lot of meters and I've never had one split like this. So I'm hoping that maybe they've changed the plastic that they're using, you know, to maybe make that not happen. I don't know if maybe this plastic just got a little dry or something that caused it to split. Again, it's very unusual. So several people have left various comments on that first video. One of them was about the contrast of the prototype meter versus the production ones. Me looking at it, I don't see much of a difference. Maybe if I got them out in the sun or something, they'd look a little different, but to me they basically look the same. Another thing that people were commenting about was the inability of the meter to read that 150 picofarad capacitor. Let's just hook that up and we can see we're reading basically 57. Now the problem with nulling out the meter, of course, is that's going to zero that out, and it's already reading 0, so that's not really going to have an effect. But what we can do, and I've had to do this with some of the other cheap meters, we can place a capacitor in parallel with the output. Again, so this is a 1 nanofarad capacitor. You can see the meter's reading basically 900. And now we can do a relative measurement. And now let's attach our 150 picofarads. There you have it. So 161. Let's just detach our leads. Let me try that one more time. So we'll zero out the meter. And here you go. 150 picofarads, dead on. Let's just try that with the other production meter. Again, I'm going to go ahead and zero this out. Look at that. So pretty much dead on. So there are ways to work around some of these problems. Again, I've had to do this with some of the other meters in the past, but I am a bit surprised that the 121 came in that far out of alignment. So another problem that came up was when I was trying to measure the 1 mega ohm resistor. If I go ahead and attach that right now, again, I doubt this meter is going to have a problem. But you can see again the settling time is quite long. That's been one of the major complaints about the meter. And of course they've released new firmware. But if you follow some of my posts on this 121, you probably are aware that I did some pretty extensive testing on the early versions of the firmware. And what I was basically finding is essentially every version of firmware that they were releasing, the noise level of the meter just kept going up, and it wasn't by a small amount. I mean, it was very noticeable, very detectable. And I think I tested all the way from version 1 of the firmware all the way up to 122 maybe, or somewhere around there. I certainly didn't go as high as the 157. I think, again, what they were doing is changing that filter constant to try to get the meter more responsive. You probably saw some of the tests where I was taking the tape eraser and I was running that by the meters, and of course the 121 was affected by that. Now they've gone ahead and added a shield around the face. I doubt that's going to affect that much, but I can believe that they changed that 50-60 hertz notch filter in hopes that they're going to speed up the response of the meter. Personally, for me, I would rather have the meter just take its time settling and come up with an accurate result. I really don't care if the meter, responds in a half a second and throws up bad data. For me, that's not really a useful meter. Of course, in the prototype meter, you can see I had installed 157, but but I don't show where I've collected any data off of that version of the firmware. I believe what had happened is when I was trying to get this thing communicating with LabVIEW using the BLE interface, I had basically upgraded to the latest version of firmware to make sure that that wasn't causing my problem, but it doesn't appear that I did any noise tests on it. So my plan is to dedicate one full episode just to testing the firmware. What I'd like to do is basically go back to version 1.0 and install it in one of these production meters and do the noise test and basically see if these two meters respond the same. And then what I'd like to do is go ahead and install the latest firmware, and we'll see how that behaves. Again, I really have no idea. I've never installed the latest firmware. Again, my goal is to keep these videos under a half an hour each, and I think we're probably close to that now. In part 3, we'll be doing a more detailed test of the 2 meters, and we'll also be comparing some of the other meters I have available with these. So stay tuned for that. Later.